talking this afternoon. And it's a great pleasure to be here with Professor Ivan de Oliveira from Brazilian Center for Research in Physics, CBPF, Centro Brasileiro de Pesquisas Físicas, from Rio de Janeiro. Professor Ivan has been working with quantum computing since the beginning of the history.
Since last century, yeah.
Yes, more than 2 decades in this subject. He is together with Professor Rochinol in the project because they are building the qubits, superconducting qubits here in Brazil. But he has been working with qubits, but in nuclear spins since 2000.
Forget about that.
So he already developed some works in nuclear spins. I know that he already has implemented algorithms in his systems already. So it's a great pleasure to be here with you. Thank you very much for accepting the invitation.
Thank you very much, Celso, for the invitation. And I was going to thank the organizer, but since I'm part of the organization, at least I'm supposed to be part of the organization. Okay, CBPF is a research institute connected to the Ministry of Science and Technology, which is in Rio de Janeiro, in a very privileged area of Rio de Janeiro. And well, as Celso said, I've been working with these nuclear qubits using Enema. I lead the group of Enema of CBPF. And this is my expertise. I'm trying to learn about superconducting qubit with Francisco Rochinol. And I'm learning a lot of things. And a few years ago, we published this book on this subject. So if anyone wants to buy the book, please don't. I have the PDF of the book. You write to me. I receive no penny from Elsevier, so I'm most pleased to forward to you the PDF, the electronic version of the book. You can write for either this address here. The top one uses not to work. The bottom one works better. Okay, so just send me a mail. I will return the book to you. Okay, let me. I told you that it would not work when I start. It is not passing. Okay, there it goes. A quick slide about the group. We are very well equipped, and we do a lot of things with NMR. That includes NMR imaging for studies of petrophysical rocks. Our 2 main lines of work are in quantum information by nuclear magnetic resonance, which is the thing I'm going to talk to you today. And we also apply NMR to study porous media, actually porous rocks, in order to learn about the petrophysical properties. So we have been very lucky to have some project with Petrobras, which is actually they're responsible for almost all these equipment here. So if you want to know more about the group, please, you can write to me. So let me try to pass this slide. Well, I'll try to pass it here. Okay, this is better. Let me start with this paper by Seth Lloyd, published back in 1993. At that time, there was no example of implementation of any quantum algorithm in a real physical system. The only things, there were a set of ideas. And then Seth Lloyd, who is a theoretician working at the MIT, on this paper here, he proposed some systems, some physical systems in which quantum information processing could be implemented in practice. And specifically, he named a number. Now it's not working either here. That's why we need quantum computation. I hope it will be better than the classical computation. So, boss, What shall I do? Just reset everything? It doesn't work anywhere. Como é que você fez isso? Agora está indo. Ah, tem que clicar lá. Ok, ok. I'm theoretician. Okay. So on this paper, he says that the physical quantum processors are made of arrays of weakly coupled quantum systems. Okay? And then computation is affected by subjecting the array to a sequence of electromagnetic pulses that induce transitions between the states. That's any quantum computing platform does exactly that. You just saw the ion traps, the same thing. And once you establish the two levels which defines a qubit, then you, in order to excite and control the qubit state, you must send electromagnetic radiation in some range. And this is true, of course, also to Enema. But here, he says explicitly that nuclear spins in a crystal lattice could be good candidates for that. Actually, well, it turns out that the best systems, most of the systems I show here, are quantum information processing implemented in liquid state samples, which is very interesting because how can you implement quantum effects in a macroscopic liquid sample? So this is one of the tricks that Enema does, and I'm going to show it to you. Very well. Then, 5 years later, 1998, the Oxford group, actually Jonathan Jones and Morska, they published the first example of a quantum algorithm implemented using an Enema system. So the first quantum computing algorithm was demonstrated in an Enema experiment. Specifically, they demonstrated the Deutsch problem, which is the very well-known problem of distinguishing between a constant and a balance function. So this was the first paper in 1998, and then people learn how to manipulate these NMR samples to implement quantum protocols. And on the same year, 3 theoreticians, also the theoreticians are very clever people, Nielsen, Knill, and Laflamme, published the first example of quantum teleportation in an experiment using a liquid of trichloroethylene, which is this molecule here. And then they show, they manage to teleport the state of this carbon to the hydrogen on a liquid sample. This is the structure of the molecule, but the sample was a liquid sample. Well, this was published in Nature, a very nice paper. And this is another example, a very successful experiment. Was part of the van der Zippen thesis, in which they built a special molecule containing 7 qubits, if I'm not wrong, and they demonstrate the Shaw factoring algorithm. So this was very nice because it showed that you can have doubt about any other product, but 3 times 5 you cannot doubt anymore, because it has been demonstrated in this paper that 15 is exactly 3 times 5 plus less 2. So this was, again, you can ask why to bother to implement these algorithms in such a small systems? Because you show the algorithm works. So in the day, Rochenau will present us with 1,000 qubits quantum chip in which you will be able to make a factorization of large numbers, you will know that the algorithm works because these people show that use NMR. So that's why these benchmark experiments are important to test the ideas. Very well. So what is NMR? NMR is a very old technique, it's over 60 years old, and is best known by the beautiful body image which the people working with medicine use to produce image from the inner body without invading. So this has been an essential tool. So people know NMR by those images, but it's much more than that. It's used in physics, in chemistry, in biology, and material science, engineers, everybody uses NMR. So the basic experiment, you take a sample, in our case a liquid sample, which you put in the middle of a magnet. For instance, this sample can be water, and the magnet, in our case, is a 12 Tesla magnet. When you do that, the protons of water, they on average, they point in the direction of the magnetic field and produce a macroscopic magnetization. And this magnetization is the observable of NMR. Microscopically, since proton has a spin 1/2, you have 2 levels, and therefore 2 levels in quantum mechanics means a qubit. So I have to manage now to produce quantum operation in a macroscopic system like that. This energy splitting here in units of frequency corresponds to 500 megahertz for proton in a field of 12 Tesla. So this is what happens when you put a glass of water, or if you put your arm in the middle of the magnet, subject to this magnetic field, you have the Zeeman split of each proton, and at equilibrium, you have a Boltzmann distribution to that temperature, which is in all the cases, at least in most experiments, room temperature. So this is the density matrix which describes this system before you start any experiment. Okay, so you put the sample there. After a while, means a couple of seconds, you have already the thermal equilibrium, and you have this description of the system. Very well. Then, what we do? We excite this system. The NMR experiment consists of irradiating this system, initially at equilibrium, with an electromagnetic wave. Actually, is a magnetic wave. We don't bother about the electric part of the wave. Exactly at that frequency. That means the electromagnetic wave is tuned to this transition here. And if you do that, then you promote transitions from the ground state to the excited state, and backwards as well. Okay? Macroscopically, what is happening is a rotation of the nuclear magnetization. So you have this classical picture of the magnetization rotating, and the quantum picture of transitions among those two levels. Okay? And more than that, if you control the duration of this electromagnetic wave, that means you apply that for a short period of time, then you can control the rotation of the magnetization. You control the angle of rotation. If you turn the magnetization to a certain angle and wait for a while, then it goes back to the equilibrium position, which means if you modify the distribution of spins between these two levels, then after a while they return to the equilibrium position. This phenomenon is called relaxation, and it is related to the interactions because the spins are not isolated. They interact with the other spins and also with the other degrees of freedom in the liquid. Okay, yeah. You mean in a tomography experiment? Well, you'll be very surprised. You have sub-millimeter resolution. Sub-millimeter. I remember many years ago, this is already maybe more than 6 years ago, USP, the University of São Paulo, they're very rich, the medicine school, they bought a Enema tomographer capable of producing image with resolution which was in the scale of micrometers. So very, very, very high resolution. The images today are unbelievable. It's amazing how they can access such a tiny bit. For instance, if I apply this radio frequency pulse for a control duration, which we call a pi pulse for obvious reason, that would mean to take magnetization from the initial equilibrium state and rotate to the opposite direction. Okay? In terms of distribution of populations, we represent like that. So we simply, with a pi pulse, you turn upside down the initial distribution. The interesting thing is that this initial distribution represents a Boltzmann distribution upside down. So the question is there any negative temperature? We can associate a negative temperature to this situation here or not? I'll go back to this point, but the expert is here, so you have any doubt, do not ask me, you ask him. Okay, so if you do that after this characteristic time, which I represent here as T1, which is called spin lattice relaxation time, this distribution here goes back to the equilibrium distribution. But the point is that if I make an experiment which lasts much less than this T1 here, can I say I have negative temperature in the system or not? Or it doesn't make sense? So I'll come back this in a while. All right, so let me show you what I call the hydrogen atom for the NMR quantum information processing, because this is the simplest system you can implement quantum information processing for a NMR system, which it may sound not much, but I will show you what this little thing can do for our careers. Okay, so is the chloroform molecule. The molecule has a central carbon atom, which is linked to 3 chlorine other atoms and 1 hydrogen. So the carbon-12, which is the carbon most abundant in the nature, carbon-12 is about 99% abundant in nature. It has a spin 0. So it's not a good sample for NMR, because without a spin you cannot make an NMR experiment. But carbon-13 has a spin 1/2, and you can enrich the usual, the chloroform you buy in the drugstore, you can, by chemical means, you can enrich the chloroform, the carbons, to over 90% abundance. That means you end up with a sample of basically all the carbons in the sample are carbon-13. And carbon-13 has a spin 1/2, and this spin 1/2 couples to this hydrogen here, the spin of the hydrogen, and then you have the simplest 2 qubits quantum information processor for NMR experiments, okay? And, well, this is the scheme of the molecule, but the sample for the experiment, as I said before, is a macroscopic liquid. And this macroscopic liquid, it's prepared by diluting the enriched chloroform in a solvent, such as the molecules, the chloroform molecules in the solvent can be considered isolated. So one molecule does not interact with the other molecule in the liquid. That is very important because otherwise I cannot write a Hamiltonian for it. I must consider the molecules isolated. And if I have these molecules isolated, then the Hamiltonian of chloroform in a 12 Tesla magnetic field is given by this one here. So you have the interaction of the carbon with the field. This interaction corresponds in frequency unit to 125 megahertz. I'm always referring to 12 Tesla, okay? Because this is the field I have there. The hydrogen interaction with the field sets up a frequency of 500 megahertz. And then you have the coupling between the 2 spins, this coupling here, which is called J coupling for obvious reason. It actually, this represents the overlap of the electronic wave functions of carbon and hydrogen. This is actually it's related to the chemical bond between the molecule, to keep the molecule stable, okay? And this is very small. It's about 200 to 250 hertz. You want to ask something? Yeah, please. Sorry? No, you have to, please, you can repeat that?
Okay. When I put the chloroform molecules in such a solvent, doesn't then suffer like ionization or dissociation?
No, not. Of course, it depends on
the solvent.
The solvent is usually deuterated water.
Okay.
It's not. It does not.
And it doesn't react. Doesn't react.
You actually you buy this enriched chloroform, and they send you 100 milligrams. It's a drop of chloroform. You pay 80,000 reais for that. These are the people who are getting money with quantum computation. The people who sell the chloroform. And then you take this drop and then you dilute in deuterated water or deuterated acetone or something like that. But the molecules remain that. And we know that because exactly we measure the NMR spectra of the system, and then we know the NMR spectra is a signature of the chemical. Okay?
Thank you.
Okay, then you have this, and now you have a 4-level system in which here I have populations, equilibrium populations, a scheme of equilibrium, what would be equilibrium population. And since you have 4 levels, then you can label this with the logical quantum states. And the logical states 0 means spin in the direction up spin, and 1 means down spin. So I have here a 2-qubit quantum processor, all right? Now I have to manage to make operation on this. All right, as I said, the initial density, the equilibrium density matrix is given by this expression here. T is room temperature, the system works at room temperature. And since the magnetic, this is a very simple explanation to do, the magnetic interaction is much smaller than the thermal interaction at room temperature, then I can expand this density matrix, and it goes like that. And since I have only 2 qubits, then the partition function is 4. So this is the initial density matrix for a NMR system of 2 qubits. And then this is interesting because now I can see that the density matrix is proportional to the Hamiltonian itself, this Hamiltonian here. And now if I apply radio frequency pulse to this system, radio frequency pulse are rotation, as I explained. So this rotation, they act only on the Hamiltonian because this is the identity operator. Nothing happens to the identity. In other words, these rotations here, which at the end of the day will be our quantum algorithm, which will be mapped to this rotation, essentially concerns to Hamiltonian transformation. And now a kind of miracle happens here. Because when I measure, the NMR observable is the X and Y components of the magnetization, okay? Remember that Z is the direction the static field is applied. But then when I irradiate the system with radio frequency pulse, what I measure at the end of the day are the components X and Y of the magnetization. So this is given by the trace of the transformed density matrix times the spin operator X and Y, okay? Which I'm representing here by sigma plus less. The sigma plus is sigma X plus I, sigma Y, and the minus the same thing. But since this operator is traceless, the miracle is that this bit here, it does not contribute to the NMR signal which is detected. And that is, in other words, I detect only the second part, which usually we call deviation, which is much, much smaller than this one. This is 1/4. This number here, if you make the calculation, this is about 10 to minus 6 compared to 1. So this little bit here, which is very, very small, is the only one which produces a detectable NMR signal. So this is a miracle because you have a huge background here of unpolarized spins. This bit here, the entropy is 1, is maximally entropic state. But when I detect only the second bit. And this is the reason at the end of the day that NMR became so useful to implement. If we do not take it into account the problem of scalability, I would risk to say that NMR is by far the best technique to implement quantum information processing because you have full control of the system. I will show you here. But unfortunately, it's not a scalable technique. Very well. So this is a scheme of what would appear if I measure a NMR spectrum in a chloroform liquid. I have 4 levels, and the selection rules here indicated by these arrows shows the possible transitions. The spectrum looks like this one. The lower doublet, I have two transitions here, this one and this one, corresponds to the carbon-13 transition at 125 megahertz, and the upper doublet corresponds to the hydrogen at 500 megahertz. Isso aqui dentro? If I should run, you please tell me, okay? In any case. All right? And actually, by looking at the spectrum, this distance between these two lines is a direct measure of this J coupling. And this is very interesting for the people who calculate molecular properties, because they are interested in know the value of this coupling to validate the model. So this is a directly measure of this J coupling, which is related to the molecular structure. In practice, this is the real thing. This is how a chloroform NMR spectrum appear. So the doublets, you can barely see here, but they are there. If you expand this picture, you can see them. So this line happens at 125, and this in 500 megahertz. One thing important to mention is that these lines here, the width of these lines, they are related to some properties, intrinsic properties of your system, but also they are related to the resolution of your equipment. And the resolution means a number of things, including homogeneity of the magnetic field, a number of different things. And in a typical experiment, the width in a NMR equipment, commercial, such as we have at CBPF, the width is about 0.1 hertz. 0.1 hertz. So you detect something at 500 megahertz with the resolution of 0.1 hertz. This is 1 part to 10 to 9. So it's a huge resolution. That's the reason why this is called high resolution NMR. Okay? All right, so the Enema Magic. I'm not going into details. There are some things now that you have to believe me, because we don't have time for that. But by means of applying these radio frequency pulse and making some algebra with the signals, with NMR, we can run the whole protocol to implement quantum information processing. We can prepare initial states, we can execute an algorithm, and we can read the final state by making quantum state tomography. That is, we can measure the full density matrix using NMR. Okay, so this is an example of a state we can produce. Initial state. You start with the thermal state, that is the Boltzmann distribution. Then you apply a sequence of radio frequency pulse and make some manipulation with the signal you detect. Then you end up with a distribution like that. Look at this distribution. This distribution has the same population in all the levels, but an excess of population on the ground state. Okay, you can do that with NMR. Okay, well, of course, this is a non-equilibrium distribution. So if I wait time long enough, it will go back to the equilibrium distribution. But look at the magic. I can write this with this density matrix here. And this density matrix is very similar to the one I showed before. It has an identity part, which is much larger but does not produce signal, and a deviation. This deviation is the excess, this bit here represents the excess of spins on this level here, right? Well, if I make a measurement, if I measure the NMR signal for this state here, what I get the signal coming only from this second term. So this is a miracle, because I have a macroscopic liquid at room temperature. And I manage to make an experiment in which I can detect the NMR signal coming from a single quantum state in that liquid. This is a single quantum state. Only the spins which are on this state here emit signal, which I detect. Okay? So these states are called pseudo-pure states. In the literature, they're called pseudo-pure states, and that's why we have this PP here. It's pseudo-pure state for obvious reason. We have this pure state here, but we have this background here. It doesn't matter since I measure only the second part. There is a huge discussion. There is no more. A huge discussion in the literature whether this is a true quantum. I don't know what means to be true quantum or not true quantum. I'm concerned only to make the experiments. Well, then from here I can do whatever I want, because if I apply a pulse of pi here, I can it's working back cells. I can manage to create other states. No. Stop again. Okay, never mind. I will run like that. Okay, so if I can manage now to transfer these populations to the other states, and then I have, if I measure the signal in each one of these, I will have the signal of spins coming in all the cases from single quantum states. All right, so the discovery of this pseudo-pure state was one of the, maybe it was the most significant discovery which allowed that NMR could be used as a technique for quantum information processing. Whatever the case, when you measure, you get a signal like that. I think in physics, this is the only signal which exists. Any system, you always have something which oscillates and decay. It's always that. There is no, nature is not very creative. So everything's like that. So what we do is the Fourier transform this signal, and then you have the NMR spectrum like that of chloroform I showed you before. Very well. Well, if I carry on the pulse manipulation of these states, I can create all sorts of states. For instance, I can create a coherent state like this one, which is separable. I can factor here these two states in the brackets, but I can also produce entangled state like this one. So once I have the pseudo-pure states initially, I can do whatever I want with them. And that's how the technique works. And what is a quantum protocol implemented by NMR on this system? It's simply a sequence of radio frequency pulses. Typically, Celso comes to me and says, I have this nice idea, and I have this quantum algorithm here. And then we take that algorithm and map that in a sequence of radio frequency pulse. Then I add a protocol to create the pseudo-pure states, and then implement the algorithm brought by Celso. And then that's what is done on these with these systems here. Okay, so I'll show you examples of things which we have been doing these years. This is an experiment of the analog of Bell's inequality violation test using NMR. And you see here The triangles are NMR experiments, and the squares, the blue squares, are experiments taken from the literature from a paper of Alain Aspect. I had the opportunity to show this to Alain Aspect many years ago. And then he said, I went away. Said, was very responsive. Okay? And the continuous line is the prediction of quantum mechanics. So you see, this is essentially what we call a simulation by NMR of another quantum system, which is a quantum optics system. And everything goes. This is something very nice on this area, because since now you have an algorithm, the algorithm works for everyone. So people work with NMR can talk to people working with optics, with superconducting. It's a common language, let's say. Okay? If you prepare a not entangled initial state, like this one, this is a Hadamard state, then it does not violate the inequality. So this is a very nice experiment we did. And then we did also the Leggett-Garg, which is the analog of Bell inequality, but for time. Bell inequality violation is related to locality, to concept of locality in quantum mechanics. Leggett-Garg inequality is related to realism. So the violation of the Leggett-Garg inequality means quantum mechanics is not realistic. Please do not ask me what the heck that means. But I'm just repeating what I read on the papers to you, okay? It's kind of very close to very exotic things, but anyway. So the inequality is this one. Tony Leggett won the Nobel Prize, not for this equality, but for his whole work. And in a spin system is reduced to these functions here, and the correlation functions are shown separate here. And it says that if a system is classically realistic, in the sense defined in the paper of Einstein, Podolsky, Rosen, the famous EPR paper of 1935, then it cannot be larger, this correlation function cannot be larger than 1. And this is clearly violated here. The blue dots are NMR results, and the continuous line is the quantum mechanical prediction is these ones, very simple, okay? So this was another experiment. So now I go back to that question I put initially, whether we can consider that situation in which I produce an upside-down distribution, Boltzmann distribution, if I can associate a negative temperature. I was going to suggest you to talk to Thaisa if she was here. But since she was not here, Celso Vilas-Boas is. So you can, any doubt, please look for him. This is very nice. This is a solid state sample. This is actually a sample used to calibrate the NMR equipment for solid experiments. It's called adamantine. So the dark spheres here are carbons, and the light gray spheres are hydrogens. Hydrogens is 100% abundant. So that means every gray sphere has a spin 1/2. But I have some 10 black spheres here. only one of them will be a carbon with spin 1/2. Okay? And that means that in a sample like that, you have isolated carbons, 13, spread in the whole sample. They are isolated from each other. And you have 100% of the hydrogens are with spin 1/2. This system, we can consider the hydrogen as a buff, a thermodynamical buff to the carbon samples. Though the experiment here is very simple. First, I keep my hydrogens in equilibrium, thermodynamic equilibrium, and invert the population of the carbon spins. And then the carbon spins are coupled to the hydrogen buff because there is that J coupling. And what we see these dots represent the states of the carbon spins. We see that after inverting the population, the carbons relax towards the temperature set by the hydrogen buff. Okay? So this is the relaxation I told you before. But now, since I can manipulate also the buff, all I have to do is to tune my equipment to 500 megahertz. Now I invert the population of the buff. That is, I produce negative temperature. And what happens to the carbons? They relax to that temperature. So as far as we can believe on this experiment, yes, we can produce a situation in which you have negative thermodynamic temperature. Of course, this is all done in a time scale much smaller than the relaxation, which leads the whole thing to the thermodynamical equilibrium. Okay, but if you do the experiment, if it lasts for a time short enough, then yes, you can define this situation. So in the paper, there are a lot of more of results. After tomorrow, you can ask Celso, not today. Okay, another work. I'll put all in once. Another work which was very fruitful was this work of work distribution. This is also in the area in which we call quantum thermodynamics. So in this work, in quantum thermodynamics, you have a definition of this function here, which is the probability of producing some work, W, amount of work W in a system, by varying an external terminal Hamiltonian. Yeah, please.
Why the terminology quantum thermodynamics and not statistical mechanics or quantum statistical mechanics?
I don't know. Right? The idea was to study thermodynamical properties under quantum evolution. I think it's very. We have to go back and see, look for who was the, maybe Celso knows that. You know, Celso, who invented this thing?
I don't know.
No, okay. So, so please find out and tell us who. Okay, and this Pn0 here is the probability that the system starts at the state n initially, and then after I make this transformation using external parameter, which lasts for a time tau, then the system goes from n to m. So this is a definition of probability of work in a forward process. This F here means forward, okay? I have an equivalent definition for a backward process, which is represented here. The interesting thing is not this function here, but its Fourier transform, which is given here, is called characteristic function. This is more interesting because there is a quantum circuit to measure this function. So what we did, we implement the quantum in chloroform. I'm still talking about chloroform. I implemented this a quantum circuit to measure this function here, and they are shown here. Okay, there's a forget about the bottom line. The forward process is represented by the blue dots, and the backward process is represented by the red dots. Okay, and then I make the inverse Fourier transform of this experiment here, and what I get is a discrete distribution of work. So I think as far as we know, this was the first example of a discrete, this is a quantum signature of the system, a discrete distribution of work in the system. And by measuring this function here in the backwards one, I can relate to other important expression in the thermodynamics thing, and including non-equilibrium thermodynamics through these results of Tazaki, Crookes, Jasinski, and the student of Roberto Serra must know everything about that. Where is he? Ah, he's here. So if anyone has doubt about that, please ask him. Okay. Well, the other things we can do by using this kind of process, we can implement also some very exotic experiment of regarding the role of time. So this is one of them. And the idea is that if you have a bipartite system, which means hydrogen, which means chloroform again, we are the kings of chloroform. We can create a correlation in the buff. So the idea is that if the buffs are, when you have correlation between buffs, then you can kind of cheat the laws of thermodynamics. And look at that. I can manipulate individually the populations of hydrogen and carbons, all right? And then I can create different temperatures on the same sample. All I have to do is to produce different populations on the system. And more than that, I can create correlations between these two buffs. And why this is nice, it's because of this paper here. This paper associates the entropies of these two systems, such as this one, to the mutual information, and more, the most important result are these ones. This is the quantum circuit, which is very simple. I'm not going to talk about this. But the important thing is that if the buffs are uncorrelated, which means alpha is equals 0, then you have the usual thermodynamical result, which shows that this quantity here is bigger than 0. And since the temperature of B is smaller than the temperature of A, this thing is bigger than 0. So this is the usual thermodynamics. But if you create a correlation, then the thing is inverted, and you have a negative result. This negative result means that the heat will flow from the cold to the hot. This is the inversion of the direction, the arrow of time. Okay? Because the usual thermodynamics, the heat always flows from the hot to the cold. All right? But if you have correlated paths, you can invert this flux of heat. And this is related to this thing called the arrow of time, which it seems that each area has its own definition of arrow of time. So concentrated only on these two pictures here, you'll see the blue dots means uncorrelated, the orange squares means correlated, and on top I have spin A, on bottom I have spin B, and remember that the temperature of A is larger than B. So in the case uncorrelated, the blue, I have the usual thermodynamics. The temperature of the hotter decreases. The dotted line here is a theoretical prediction. Okay, so you have a cooling of the hotter and a heating of the colder. Spin B, which is colder, increase temperature. But when I correlate, the thing is inverted. I have here the hotter getting more, increasing the temperature, and the colder decreasing the temperature. The process is cyclical, so there is always a cycling aspect of this. But the point is that you can indeed, you can invert the direction of the heat flow on this system. And we have done a lot of things on this using chloroforms. So we are very grateful to God to have invented this substance, which guarantee many years of work. So I still have 10 minutes, boss? Okay, I will quickly speak about another interesting NMR quantum information system, which are nuclei which have spins larger than 1/2. 1/2 spin nuclei are considered point charge. They have no dimension. This is of course, an approximation. It's a model. It's not the real thing. I don't know what the real thing is. I know what I learned in the books. So the book says if the particle has spin 1/2, you don't have to consider the extension of charge distribution. So I do not invent the rules. I just follow them. But if the spins are larger than 1/2, and there are many, you have spins 1, 3/2, 5/2, 7/2, and so on, then you must consider the charge distribution. They cannot be considered pointless point charge, okay? And the situation is like that. The charge has a certain distribution. And of course, in this case, you have clearly an orientation of this charge distribution in respect to the electric field produced by all the charge on your samples. In this situation here, the picture on the left has an energy bigger than the picture on the right, because here you have the distribution pointing to plus. Of course, the nuclear charge is also positive, and then the energy here is larger than that. Very well. So this must be included in the formalism, and you can map, formally you can map these space variables. Now we are talking about space distribution of charge, but they can be mapped into the spin representation using a very useful theorem of quantum mechanics called the Wigner-Eckart theorem. So the Wigner-Eckart theorem allows you to represent space coordinate operators to map them into spin. It's very useful. I think it's the only useful theorem I have seen so far. This is really useful. And then you end up with this Hamiltonian here. You have the magnetic interaction, which I showed before. And now we have a second term here due to this charge interaction. And the electromagnetic multipole, the simplest one for NMR to represent a charge distribution is the electric quadrupole moment. So the electric quadrupole moment is that number which represents space charge distribution of nuclei, okay? And the electric quadrupole moment interacts with the electric field gradient. This comes straight forward from the electromagnetic energy when you expand. So the electric field gradient is represented by this little q here, and the electric quadrupole by this capital Q here. So this is a property of nuclei. This is a property of the environment of your sample. Anyway, this is a constant, okay? Given a spin number, this is only a constant. The important thing is now you have a quadratic term in the Hamiltonian. So this quadratic term is very useful to make a lot of experiments. And sorry, here is again for an example for spins 3/2, for instance 23 calcium, and you have again 4 levels. But now the transition rule says that you have transitions only between adjacent levels, and so your NMR spectrum has only 3 lines instead of 4. Anyway, you have 4 levels, and then you can label them as a system of 2 qubits of quantum information. You can play with that. But now you have a quadratic term in the Hamiltonian, which allows you to study different stuff. This was the use of quadrupole nuclei for quantum information processing was first noticed by the Indian group led by Anil Kumar. And on this paper, they work out everything, including all the logical gates and so on, and show that you can use this system also to make quantum information process. They only left out the technique to implement quantum state tomography to measure the density matrix, and that we could do. Was a PhD thesis of Fabio Bonk, and here are examples of quadrupole nuclei density matrix measured by the technique we developed, and the corresponding NMR spectrum. Well, this is, as I said, this is not scalable, NMR is not scalable, but you end up with something which is useful to, you just have to find a problem. In this area, in physics is a thing like that. You find the problem after you have the solution. First you have the solution, which is quantum information theory. Then you have to find the problem. You have the technique, which is NMR. Then you have to find the correct problem. And there are many problems which can be studied with these quadrupole nuclei because you have a quadratic term. For instance, they can be mapped in Bose-Einstein condensate. Then you can study Bose-Einstein condensate properties with NMR, which sometimes is very, very useful because it's simple. It's much simpler to implement. It may be very helpful to, for instance, Vanderlei Banhato. Okay, in summary, with NMR you can prepare initial pseudo-pure states. You can implement a set of universal quantum gates. I did not show you that, but believe me, we can. You can implement all the fundamental quantum gates. You can read the final state by means of quantum state tomography, and with that you can demonstrate all kinds of things concerning quantum algorithms, quantum tools to measure the quantumness, or the degree of quantum correlation of system, and or a sort of a box with many tools. All that in a small, non-scalable system, and in a time smaller than the natural decoherence time. By the way, even under decoherence, we can implement correction code errors. We have demonstrated that. You can leave the system to decohere, and then you implement some protocols to correct the state, which is fundamental for the development of quantum computation, to have protocols to correct errors. I spoke too much. Thank you very much.
Thank you very much, Professor. Now, questions?
Some professor, it's interesting this topic. Just to understand it, so you have a system of 2 qubits that is defined because of the spin of both of the carbon and the hydrogen. Is it possible to do the same but with 3 atoms?
Yeah. We can, up to 4 qubits is relatively simple.
Okay.
The problem is beyond that is it becomes rather difficult. I think the largest system was produced by the group of Raymond Laflamme in Canada. They managed to entangle 13, the same as almost the same, the atomic trap. So they make an experiment and show that they were able to entangle 13 qubits. But as far as I know, they did nothing with those entangled qubits because the situation becomes really complicated. You no longer can make a quantum state tomography because you would take a huge amount of time to do that. And so definitely increase the number of qubits in NMR experiment is not a priority. I think the nice thing is to try to find interesting problems which can be studied in this smaller system. But up to 4 qubits, the problem is many times the problem is to find the molecule.
Exactly.
You need the molecule. The Shaw algorithm factorization, the molecule was built, I think IBM or some company, I don't know, these people can do anything. And they built that molecule for the experiment. It had 7 qubits only, which is quite complicated already.
Okay, but in this case, you are working in a very low temperature, right? In order to
room temperature. All room temperature.
Yes, but you showed me that in the magnetization term, you have the field, the magnetic field.
Yeah, the magnetic field is at 4 Kelvin. Yeah. The magnetic field is at helium temperature. It's a magnet. Is essentially a thermal flask. You have helium, and then you have the magnets inside. The magnets kept because it's superconducting magnet. So you have the 12 Tesla magnet inside the liquid helium, and the cryostat has a hole in the middle, and the sample goes into this hole, and that at room temperature all the time, room temperature. If you cool the sample, you destroy the resolution. You no longer it's a bit complicated, but I mean that nice resolution you can see. I mentioned resolution of 0.1 hertz in 500 megahertz. If I cool down my sample, I lose this resolution. I no longer have that. So it must be done it's an exotic case. This quantum computer only works at room temperature, contrary of all other quantum computers.
Okay, thank you.
Okay, but you need a very strong magnetic field, right?
Yeah. Well, we can do with. You don't need to be that strong. The intensity of the magnetic field helps. Because in some samples, the intensity you can resolve some lines. When you get a complicated spectrum, if you have a more intense magnetic field, sometimes you can get resolution, a better resolution. So
good.
They have these magnetic fields of 20 Tesla, which is a beast, the size of this room here.
Okay, thanks.
So thank you a lot for your lecture, Professor. And my question is the following. If you have to select the greatest challenge in our system, what would be that? It's like the number of qubits, for example?
Yeah, the number of qubits, I cannot say it's a challenge because it's not possible. First, because there are no molecules, there is no natural molecules with 30 qubits, for instance. You cannot have that. And even if you have that, the spectra would be so complicated with so many lines, which would be essentially impossible to make any analysis. So that's interesting thing is that when Seth Lloyd published that paper, he did not know that. So NMR at that point sounded as a promising technique for large-scale quantum computing. So people learn that was not possible along the way. And what in my vision now, what is NMR today? NMR is an excellent technique to make tests on a small system, because on a small system you have full control, and if not for quantum computing, you have these fundamental questions. For instance, in this area of quantum thermodynamics, which there are many interesting questions which can be studied, and this is the where NMR should be applied. And do not worry about scalability. But let me tell you something which I consider very profound. When you have, for instance, superconducting qubits, which is a scalable technique and very promising, what you must have at the end of the day, you must have a two-level system. So the hardware with the Josephson junctions, they are built to have two-level system. And after that, there is no fundamental difference to NMR. All you have to do is to apply sequence of microwave, in the case is microwave, because they are gigahertz frequency, to this two-level system. So NMR is a good system even to study the superconducting system. Because once you have the two-level system, it becomes a spin. It becomes a spin. And spin is NMR, right? I think this is very interesting. At the end of the day, everything is a spin.
So thank you, Professor.
Thanks for the talk. I have the following question. So you have your ensemble of molecules, and you make a pulse. At the end, you have a state that is nearly the maximally mixed one, plus some little contribution from the state that you want to make. You say us that the magic of NMR is that you can measure traceless observables, so then the maximally mixed part goes away, and you only have at the end the small part. But for example, if I want to measure some fluctuations, I will need to measure a square of in this case, the Pauli matrix, which is the identity. So if I want to measure a fluctuation, the whole state will contribute the maximally mixed part, and the small contribution. So at the end, the fluctuations will be big. And my question is, how do you how do you make the claim that you are certainly sure that you have your state, the one that you prepare? Because the fluctuations is big. So how do you
Actually, you are referring to possible errors in the signal you measure.
Yeah.
No, even that tiny deviation is still very large. There is no, essentially, the signal you measure, you cannot see the error bar on them, because it's yet, although small, the sensitivity of the equipment and the whole process, because we don't look at the bare signal which is coming from the sample. That is measured like induced voltage in a pickup coil, and that signal goes to a chain of electronics which makes a lot of averaging amplification and so on, and what it comes to the computer screen, it has no longer anything to do with the initial signal. It's amplified many times, and there is a whole chain. So there is no question about the error on this measuring thing.
But even at the theoretical level and not like neglecting of the electronics, the method, if you want to like make an estimate of the fluctuations in an ideal case, you have that the fluctuations are big, like quite big, because you have to consider the maximally mixed part. So even like neglecting all possible errors coming from electronics, so conceptually, like is a big chance that you don't prepare the state that you are like trying to prepare.
We have always to, at least on the experiments we run, the first thing to do is to check that thing you are saying. So if I say I create a entangled state at the beginning, so I do quantum state tomography to check whether that state has been really created. So we check everything. So in some case, we have done quantum state tomography along the whole protocol. Every step we just to follow and to be sure the states is what we think they are. If you have a too small system, then the experiment becomes very complicated, because then you have to repeat many times. And but on these standard samples, the miracle of chloroform is there is no problem. So no doubt about that.
Okay, thanks.
Okay.
More questions?
Hi, thank you for your talk. I was thinking, you mentioned about error correction, and generally error correction relies on redundancy, so you need to add qubits. So is that the case for NMR, or do you circumvent that because of scalability?
Yeah, some protocols of quantum error correction has been tested with NMR. Phase error correction. Raymond Laflamme was very engaged in that. He has a lot of nice work concerning error correction. I think because he has some protocols invented by himself, and then they tested a lot. Raymond Laflamme, he was one of the few physicists who believe that quantum computing on large scale would need NMR. So even I don't believe that, but Raymond Laflamme was sure that I think because of these, we don't have the sample, but we have the perfect tools. I think these spins manipulation you can do. If you write on your notebook a density matrix, you invent any density matrix. It must be a density matrix, and give to me, I produce on the system. Anyone. So I put those little numbers in every position on the density matrix I want, by playing with these spins rotation. So it's a very powerful technique, but it's no good for scaling quantum computing. But as I said, we can learn a lot, because on a system with 1,000 qubits, I can test, I can simulate that with NMR to know whether it's going to work or not. So, dinner time?
Are there any questions? No? If it is not the case, let's thank again Professor
Thank you very much,
Ivan.
people. Thank you. Celso. Obrigado.